In the past decade, numerical simulation has been clearly established as a new research discipline, one which complements the traditional role of experimentation and theory. Large-scale computer simulations performed on supercomputers, such as the Cray YMP, have enabled scientists and engineers to extend the limits of their understanding in ways that were previously thought impossible. Many problems that are solved by supercomputers today could not be performed by any other computer in a reasonable time. The purpose of this videotape is to describe the beneficial impact of supercomputers in several facets of everyday life. Let's look at a few examples where supercomputer technology has been an essential component in helping scientists and engineers do their work. Automotive companies around the world are presented with the challenge of designing safer, better automobiles at a lower cost and in a shorter time period than ever before. Consider BMW's project to optimize the design of an engine connecting rod used in actual production cars. Through supercomputer analysis, BMW engineers were able to reduce the weight of the part by 8% and reduce the working stress characteristics of the component by 20%. The result was a stronger, lighter component that was designed at a substantial cost savings over its predecessor. This example from Ford Motor Company compares simulation with actual behavior for a side impact crash. Each actual crash test costs over $200,000. This test produces results for only one angle of impact, with limited ability to observe internal dynamic effects that occur during the crash process. Computer simulation costs are an order of magnitude less and provide the flexibility to change all of the crash parameters. Until recently, scientists have exclusively followed the ancient procedure of trial and error for developing new materials and drugs, or understanding basic life processes. This is a costly process in terms of both time and money. To reduce these costs and hasten the design process, scientists are turning to a numerical solution to predict the behavior of molecules. The world's largest chemical company, E.I. DuPont de Nemours, recently used its Cray supercomputer to study the properties of a catalyst that was proposed for use in the production of Kevlar polymer fibers. Through computational analysis on the Cray system, it was discovered that the proposed catalyst would achieve less than 10% of its desired effect. Based on this knowledge, the direction of the experimental research was altered, resulting in a direct saving of several $million. All of the major aerospace companies and research laboratories in the world use supercomputers to perform computational fluid dynamics and structures calculations in support of the design of advanced air and spacecraft. The United States NASA Space Shuttle program has made heavy use of supercomputers to redesign components of the solid rocket boosters and main engine. Analysis and testing of the Space Shuttle main engine focused on evaluation of the fuel turbopump blades and the high-pressure oxidizer turbopump. To be effective, the analysis had to be timely and accurate, but also had to be integrated with testing to provide input that would influence hardware design and management decisions. NASA scientists recently commented that computational analysis of the type provided by their Cray systems has helped to restore the space shuttle to safe flight status, as witnessed by the successful September 1988 mission of the redesigned shuttle Discovery. In the past 20 years, the development of appropriate numerical methods, computer programs, and supercomputers has made it possible to calculate the future state of the atmosphere and the oceans with reasonably high accuracy in a timely manner. It is impossible to fully understand detailed weather phenomena, such as this tornado, through observation alone. Using a Cray supercomputer at the National Center for Supercomputer Applications at the University of Illinois, Dr. Robert Wilhelmsen and his team recently animated the evolution of a thunderstorm crossing the plains of Illinois. The model is able to accurately predict severe storm details, such as future values for wind speed, air temperature and pressure, water content, and updraft rotation. Likewise, large-scale numerical simulations of atmospheric pollution phenomena performed on supercomputers are proving to be much more accurate than those performed with simpler models executed on smaller computers. For example, a three-dimensional tracer model to simulate the dispersion of nuclear debris from the Chernobyl nuclear reactor accident was conducted at the Canadian Meteorological Centre in Dorval, Canada. The hemispheric models were executed for a 4-week period and show a high degree of correlation with the observation. The animation, also done with the Cray system, provides a visual record of the effect that the Chernobyl accident had on the world. In the past decade, supercomputers have helped establish numerical simulation as a third research discipline, which complements theory and experiment. The benefits of supercomputer analysis are already being realized by saving time and money, creating better designs, improving health and safety, and avoiding catastrophic failures. There is little doubt that in the next decade, every technologically advanced nation on the Earth will acquire and use supercomputers in all aspects of industrial, government, and academic research.